yours. Okay. Thank you, Joseph, for the introduction, and thank you all for inviting me here. It's a pleasure to be back in Paris and Saclay to see old friends and to meet some new friends as well. So Joseph told me I should give a talk that's mostly colloquium level stuff, and then at the end for the mathematical physicists, I'll give you some mathematical physics, so there's something for everyone. I'm hoping that the level will be such that everyone can appreciate what I have to tell you. And indeed, most of the talk will be about my new book that I just published in this past spring. The title is Quantum Measurement Theory and Practice, together with my co-author Irfan Siddiqui, who's at UC Berkeley, also in California. Okay, good. So what I'm going to tell you about today, so this is the introduction. I'm going to give you a little bit of introduction for who I am, where do I work, what do I work on, and tell you about the book, and then some new theoretical results based on mathematical physics about optimal control theory for continuously measured systems. So this is the plan for today's seminar. So where is Chapman? So I moved, for most of my career, I was at the University of Rochester in New York, and then about going on 4 years now, I was asked to come to this university, Chapman, and direct their Institute for Quantum Studies, which is where I am now. And they're just south of Los Angeles, between here and San Diego. That's the university. It's in the city of Orange, within Orange County, which is somewhat confusing. What is less confusing, it's near Disneyland. So if you know where Disneyland is, it's very close to there. And I live down here where all the hearts are in Laguna Beach. I said if I'm moving to California, I live by the ocean. And so I have a wonderful house down there in Laguna Beach. So it's a great little private university that I like very much. And if you're there, ever want to come visit me, you're all welcome. Just send me an email and I'd be happy to host you. What do I do? So I work on a bunch of different things. Today I'll be telling you about maybe my main interest, quantum measurement and control. This is something I've worked on for a long time. And then I also work on topics of quantum metrology and precision measurement. How do you use quantum physics to make measurements more precisely than you could with comparable classical resources? I also work on topics in quantum thermodynamics, both on the mesoscopic systems. So I actually started my career. I met many of the people that are in this room back when I was a postdoc more than 20 years ago, working at the University of Geneva with Marcus Bodeker. And this is, I continue this work on mesoscopic physics. And then going into more general topics in quantum, what we call quantum energetics these days. And then also I'm interested in foundations of quantum mechanics, and that's really the main focus of the institute that I work in at Chapman, are these foundational questions in quantum mechanics as well. So those are my research interests. And what I'm going to tell you about today is about this book. So I started writing this book. I'll tell you more about the history of that in a moment. But it's together with Irfan Siddiqui. And here's a nice advertisement from Cambridge University Press, who published it in just this past spring. So I'll tell you more about that in a moment. So here's the timeline of the book. You see at least one person in the audience here. Daniel Esteve appears on the very first picture of the timeline. I think we were at a conference in Japan, if I remember correctly, in 2019. And we were sitting on the bus together, and Daniel said, "Andrew, you've done all these wonderful things. You published all these great works, but nobody knows about it. You need to write a book to tell the world about all of this stuff you've discovered," with Irfan. And I think independently he was working on Irfan as well. He was at some other conference around the world. I think, "Irfan, you should really write a book about quantum measurement." And so at some point, Irfan is like, "Andrew, we should write a book." Okay, but you see, just the desire to write a book is very, very different than writing a book. And so you see all these points in the timeline along the way, all the things that happened in between, including the COVID pandemic, the lockdowns, and actually being locked in your house for a long time is a good excuse to write a book, right? Because what else are you going to do? Anyways, so at the end of it, we have our complete draft in 2020. It still takes forever, but the book got published this past spring. Okay, so that's the timeline of the book. Good. So this is when we thought we were done. We're celebrating the writing of the first draft in 2022. That's where I live here in Laguna Beach. Beautiful palm trees, a nice resort there. Okay, so what is the book about? So the book is divided into three basic topics. It's meant for sort of the graduate level and also for other researchers in the field. It's divided into fundamental principles, advanced topics, and applications and implementations. And that's the subject flow of the book. And just to give you some teasers, here are some questions that I can put up on the screen. You can take a look at those questions. And if any of those questions look interesting to you, but you don't know the answer to them, it's a good reason to buy the book and to learn the answers to those questions. Okay, so, but there's a lot of fascinating stuff going on here about these continuous measurements, about amplification, stuff that really doesn't show up in any books. And so I think we were able to fill an important niche in the literature. And I'll be telling you about some of these topics in the course of the seminar. Okay. So what's the basic summary and subject matter? Well, this is the blurb sort of setting out the purpose and the scope and the mission of the book using a physics first approach to quantum measurement. So very often if you read about quantum measurements, sometimes you get into very mathematical descriptions, sometimes you get into very philosophical descriptions, but very few references tell you how it works from a physics first perspective. Here's an experiment. Here's some phenomenon in the lab. Let's understand that. And only after we understand that, do we begin to fill in the mathematical framework, we begin to fill in the philosophical framework, and then talking about some of the topics that are dealt with in the book. Okay, and it has to do with these wave functions that like to keep collapsing and trying to understand what is this collapse process all about? What's it really all mean from a physical point of view? Good. And so we begin with the cardinal properties of textbook quantum measurement you've all learned from your quantum mechanics classes. So these are what I call the three cardinal properties. Its projective nature, its irreversible nature, and its instantaneous nature. And all of these are part and parcel of the sort of knowledge we've been handed down. So it's projective in the sense that a perfect knowledge of the property we're measuring is associated with the projection state onto the observable eigenvalue. It's irreversible. So this is a quote from Wheeler paraphrasing Niels Bohr, which I like a lot. We're dealing with an event that makes itself known by an irreversible act of amplification, by an indelible record, an act of registration. Okay, so once you make a measurement, you cannot undo it. And it's instantaneous. And so I think this is lightened in the writings of Einstein, but it's explicit in the writings of Heisenberg. He's envisioning an experiment, a scattering experiment, where you have a reflected and a transmitted wave packet. The experiment at the position of the reflected wave packet thus exerts a kind of action, reduction of the wave packet at a distant point occupied by the transmitted packet, and one sees in this action it's propagated with a velocity greater than that of light. Leading to the conclusion must be instantaneous. Okay, good. And one of the main messages I'll be telling you about in the seminar is that we can talk about other kinds of measurements that break all of these cardinal properties. We can make a measurement that is no longer instantaneous, that takes place over a period of time. It breaks irreversibility, it can be probabilistically reversed, and the projective or disturbing nature can be minimally disturbing. I can turn down that disturbance as a function of my measurement. And what do I mean by a generalized or continuous measurement? Any situation where there is some imperfect correlation between the state of the quantum system and the reading on the measurement device, the meter. Okay, and we'll go into some physical examples here shortly. Okay, and so the first chapter of the book is really talking about the founders of the field and gives a little history and puts the field in a philosophical context as well as a physical context. Talking about the founders of the field, going up through development up into the 1950s, and then the reexamination of some of the fundamentals of the field, starting with the work of David Bohm, and then followed by the work of John Bell, and then going into what we call the quantum information era. Okay, so it's mainly historical and motivates the subject. And then going into some of the basic physics of the quantum physics, just reminding you about some of the more elementary results, talking about this is what we call the cigar of Otto Stern. The apocryphal story, anyway, is that the silver atoms on the Stern-Gerlach experiment was developed by Stern's cigar smoke blowing on it, blackening the silver, so you can see this double splitting of the spinning electron, shown famously on this postcard they sent to Niels Bohr, showing the results of their experiment. Okay. And this motivates also some of the main results from quantum physics. Given a superposition, it's impossible to predict which outcome will occur, telling us that uncertainty is fundamental and results in quantum noise. But what we shortly learn is that there very often are measurements that don't fit into this sort of standard textbook kind of predictions or explanations of how measurements work. So one example is the spontaneous emission of an atom. But here is a famous example that should be familiar to our Saclay condensed matter friends. The example is what we call a null measurement. So wave function collapse can also happen when something does not happen. What do I mean by that? Well, there's a famous experiment here. I can think about a so-called superconducting phase qubit with a Josephson junction and a capacitor and some inductors, where I have microwave control, but also a readout of this device. And the way it works is an effective metastable potential is created with the Josephson junction circuit, such that the quantum superposition exists between the ground state and the first excited state. Of course, they can principally be higher states. But this is a metastable system because of the way this circuit is tuned in terms of its energetics. And what can happen is that a particle the pseudo particle that is prepared in the ground state effectively cannot tunnel through this barrier on the timescales of the experiment. But if you're up here in the excited state, it can tunnel through on the timescale of the experiment. So what happens is essentially you prepare some superposition of the ground and excited state in this preparation stage. And then by making a tilt of this effective potential, I can effectively lower this barrier and see, does this particle tunnel out or not? So there's a selective tunneling that occurs. But you don't do it for a long time. You only sort of tilt the well just for a short time and then tilt it back, right? And then you check, did it escape from this well or did it not? And one of the amazing things about this experiment is that this describes a continuous collapse to the ground state of this double well system, provided that you don't detect a tunneling result at the end. So the fact that your detector readout does not give you a click means that something happens. And it's very similar to this story from Sherlock Holmes, Arthur Conan Doyle's fictional character, in this nice exchange between Gregory, the Scotland Yard detective, and Sherlock Holmes. Gregory says, "Is there any other point to which you would wish to draw my attention?" Holmes says, "To the curious incident of the dog in the night time." Gregory says, "The dog did nothing in the night time." And Holmes says, "That was the curious incident." So it's exactly the same thing here. The fact that the detector gives you nothing, the fact that the detector is silent, is giving you information. Something not happening means that something happens. And so what that describes is a continuous collapse gradually to the ground state of the superconducting qubit in a way that we can quantitatively predict and then test in experimentation. Okay. Other topics we cover in the book, topics of what we call weak measurement and also weak values, where you have a very weak interaction between a meter and a system, and then by being able to measure that meter, you can extract a small amount of information about the quantum system, but it also turns down the disturbance. You don't get a complete collapse of the system, but a slight jiggle or perturbation onto the quantum state. And then if you also do what is called the post-selection on the original quantum system, you get something called the weak value predicted by Yakir Aharonov and colleagues. And that effect is actually very interesting, and I've been working on this effect for many years. But one of the more famous things that I've worked on is this optical interferometer, where you imagine you have a very tiny motor that tilts the deflection of this beam, and if you have the optics just right, what happens is you only get a small amount of light that comes out of the so-called dark port of the interferometer, but the shift of the mean position is very, very anomalously large. Okay, so this is a reflection of the wave interference that goes on in this experiment, and so this is also related to the so-called weak value effect that we cover in detail in the book as well. Okay, and then one of the, I think, very profound aspects that people have really only been able to understand in the past few decades is we can ask ourselves, what limits does quantum mechanics put on amplification? What's the best amplifier you can build? And our friends here in the condensed matter group do this very well because that's their business of trying to build these really very sensitive amplifiers. And so how do you go out and do it? What is the theoretical limit? And then how do you actually build it in principle? So typically we have a schema. There's a quantum system. There's some kind of meter or pointer it gets coupled to, a low noise amplifier that we describe in a quantum formalism in terms of input and output operators. Okay, so this can be done in terms of linear response theory, having quantum theories of linear response we can develop, starting with Kubo formulas for responses. But then once you have those kind of theoretical limits that tell you what's the minimum way you can, the best way you can extract the information from the quantum system without disturbing it, it turns out that there are some nice theoretical results you can derive from very simple starting points. One of the results we talk about in the book is that you need the reverse gain of the amplifier to vanish, as well as the real part of the cross correlation between the input and the output fluctuations to vanish. And if that happens, then you get an ideal quantum measurement without talking about necessarily all the microscopic details of the system, as long as it is in the linear response regime. And so these describe a situation where the noise from the output circuit does not induce back action, and there's a degree of similarity between the input and the output states of the amplifier, so that there are no extraneous internal degrees of freedom that could extract information from the circuit that we cannot see. The idea is we want to be able to see all of the information. It should not be hidden in unobserved degrees of freedom of the environment. And you can derive a very nice formula between the rate that you extract information from the system versus the ensemble rate of decoherence. And if you saturate this inequality, you get a quantum limit amplifier. So this is a very general theoretical result, but it doesn't tell you how to build one of these things. What do you actually do in the laboratory to make one of these beautiful amplifiers? Well, and we have a whole chapter on how to build these things using Josephson junction technologies and circuits, either in a three-dimensional geometry or in a two-dimensional planar geometry. And then we get into some of the physics of measurement. Okay, so once you have these devices, once you have these quantum limited amplifiers, what can you do with it? And so this takes us into the topic of, can a measurement be continuous? What does that mean? How can I talk about a continuous measurement? And this brings in the idea of what's called the quantum trajectory. So if we accept that noise is fundamental to quantum measurement, the quantum continuous measurements come in two basic types of measurements. We call these diffusive measurements or jump measurements or quantum leaps. And diffusion comes into play when there's a quasi-continuous stream of data coming to the detector, whereas jumps usually occur when the information comes with a sudden click or in packets. Okay, but both types allow the tracking of the quantum state as a quantum trajectory in time. And so these are the two types of examples. So one is where I have a continuous measurement record that's discretized in some small time units here, that this would be the output of some macroscopic measurement apparatus you can see on your oscilloscope. And this is the associated quantum trajectory of the state that you would then ascribe given the information you're reading on this detector. So that would be the diffusive type. And over here is a classic experiment going back to the 80s about quantum jumps, where you're looking at fluorescence effects if you're driving at some three-level atom. And you see the jump of these quantum signals, and these are these jumpy quantum trajectories. So let me give some examples. Here's a physical example. This is an example from mesoscopic physics. I think about a quantum point contact as a charge detector. Now, what is this? So here's an example of a two-dimensional electron gas where I can confine electron motion into a two-dimensional plane, and then metallic top gates then further confine the electrons into other structures. So here, this is effectively a zero-dimensional object called a quantum dot, and there are actually two of these. So they're actually, it's called a double quantum dot. And so a single extra electron in the system can either occupy the left or the right dot, or it can tunnel back and forth between these two situations, forming a coherent quantum state. And the way this is read out, what's the readout process, is simply the fact that recognizing that this electron has a charge degree of freedom, so we can utilize that charge degree of freedom and read out the charge degree of freedom via the capacitive coupling to a nearby quantum point contact. So this is simply a little resistor where I apply voltage between a source and a drain. I measure the current that flows through this little channel, and the current is very sensitive to the surrounding electromagnetic environment. So if the electron is left versus right, it constricts this contact a little bit and changes the current. Okay? And so we describe that if the electron is, for example, is left or right, if I call that 1 or 2, the current slightly changes between two values, I1 and I2, but these values are very small. The difference is very small. Delta I is very small, and so it takes time to measure the fact that it's 1 versus 2. Why is that? Because there's a noise associated with the readout process. There is a background detector noise, in this case electron shot noise of some spectral density, and I have to measure long enough where I can distinguish that signal, that I1 versus I2, from the fluctuations behind it. Because the signal essentially grows with the time, whereas the noise grows like the square root of the time. There is some new time scale associated with distinguishing what we call the characteristic measurement time, which is a new time scale that enters into the mathematical description of the continuous quantum measurement. So essentially the ratio of the spectral density of the shot noise divided by the difference between these two currents squared. Okay, and that becomes an important new time scale in the mathematical formulation. Okay, so that's a physical example of a continuous quantum measurement. And what happens is that once we have this continuous measurement, we can have this idea of quantum trajectories. And what's the idea? It's possible that by measuring in real time the data coming out of this experiment, to track what the quantum state is doing continuously in time. So I have a little movie here. So the idea is that as I collect data here, I can then infer what the quadratures, for example, of a two-level system are as a function of time. And rather than immediately collapsing either to the excited state or to the ground state, there is some stochastic dynamical process that takes you there. So gradually I'm collapsing to the sigma z equal +1 state, and that the associated sigma x quadrature is 0. So I start in sigma x, I eventually collapse here to z is +1. Now, if I did it again, I would get a different quantum trajectory, typically, and it might collapse down here to z equal -1. And the probability of that is given by the initial state. And so what's interesting about this kind of dynamical description, it allows us to peer into the inner workings of this collapse process. It's no longer a black box that you can only talk about in philosophy books, but we have a rigorous mathematical theory. And what we can do is then check that this is the correct description. And the way we do that is we can stop somewhere along the way, and then you do conventional measurements to check, is my prediction of what the state is actually reflective of what the subsequent experiments tell me? So I can then verify this quantum trajectory as a function of time. Oh, yeah, and so then we can begin to write down mathematical equations that describe these. I'll talk a little bit more about that shortly. Okay, and so this is one of the, I think, pioneering experiments we did back in 2013 with Siddiqui's group, where you can actually measure as you're driving the qubit at the same time, and then be able to measure both the ensemble average behavior in green, but also the shot by shot in a single realization of the measurement, being able to infer these quantum trajectories in magenta. And as you drive it, you can have the combination of the Rabi or the Schrodinger evolution together with the dynamics from the quantum measurement coexisting together. Okay, so the analogy I like to give is that you imagine you have a cage of butterflies, and you let the cage out, you open the cage, and the butterflies start flying around, and either they land on one of two trees. And so the old way of saying it is that I know which tree that the butterfly landed on, but now we have further information, we can say. We can now track the path of this butterfly as it goes from the cage to one of the trees, and be able to say a little much more about the physics of the process. So that's the analogy that I like to give. Okay, so now we can get in more into the mathematical physics part of the story. And one of the formalisms that my group has been developing over the years, gosh, this is now more than a decade ago, is we developed a new kind of path integral approach to describe these stochastic quantum trajectories. We call it just the stochastic path integral approach. And the idea is we use information about how the detector responds to the quantum state, depending on what it is. We parameterize the quantum state with some set of variables. We'll just call them Q here. And the readouts, the thing that you measure in the laboratory, would be described by this variable R. And in the limit that we have essentially what we call a Markovian process, where the measurement now is only indirectly correlated to the measurement in the future through the disturbance of the quantum state, we can build up the net probability of all the possible quantum trajectories via some product over conditional probabilities and probabilities of the detector outputs. And when you work through the mathematics, you can write a very nice formula. You introduce some auxiliary degrees of freedom p, which are conjugate to the quantum state variables, which plays a formal role of a canonical momentum. And you write some action that looks like this, where you have some dynamical term and some what we call the stochastic Hamiltonian, which is it's not the same as the normal Hamiltonian, it's different. And then you integrate over all these p's, and these are then paths that connect, for example, some initial states to some final states. And the way we derive this is we essentially double the quantum state space. It gives us a canonical structure on this theory, and then we can express the joint probability of all the possible measurements of trajectory as this path integral. And once you have the path integral, there's some formal similarity to the Feynman path integral. And if you extremize over the paths, we try to look for the most likely paths, you get some kind of ordinary differential equation when you minimize the action, which tells you the most likely path from going from an initial point to a final point. And so this over here on the right-hand side, this picture tells you for just a simple collapse process, if I give you the time and I give you the initial and the final points, the theory predicts this yellow dashed line as the most likely path to collapse to the ground state, for example. And then the histogram tells you all possible quantum trajectories that go from, say, this point to that point. And then by looking at the clustering of the trajectories, the magenta line tells you the experimentally reproduced most likely path, which is clearly very, very good agreement with the theory. So this is a way of characterizing what's the most likely way the quantum system collapses from one point to another. Good. And so the way we do that in the experiment is typically by grouping the distance between nearby quantum trajectories and then finding the path, the trajectories that are closest together in order to create this path. And so you see both the collapse in the z, but also the x block coordinate for a qubit. Okay. Yeah, in the driven case, you can do some of the same thing. And so in principle, you see that these paths become very, very weird, right? So these are the same initial and final states, but with different times in between. And you see that these paths become quite different, but nevertheless, we have good experiment agreement with the theory. Okay, we can do all kinds of other things as well. So one of the other topics that I like to talk about is rethinking Heisenberg uncertainty. So the traditional statement of the uncertainty principle is that the uncertainty of the position and versus momentum measurements of the same quantum state is bounded by Planck's constant reduced over 2. But you can ask other kinds of questions that is not really probed by the traditional Heisenberg uncertainty. For example, I can ask, suppose I had an experiment where I jointly measured both the position and the momentum of the particle at the same time, right? So if you look at the sort of traditional formulation of quantum textbooks, you'll say that's simply a nonsensical question. You can't do that. But nobody is going to forbid me from putting two detectors on the same quantum system, one that probes one degree of freedom and the other that probes another non-commuting degree of freedom. I'm allowed to do that. No one's going to stop me from doing that. I can turn both the detectors on and see what happens, right? And indeed, you can do that. And what's amazing about that is you see that and this indeed has also been done in an experiment. So I even have a paper about this when I was a postdoc more than 20 years ago. But the interesting thing is if I align both of my measurement observables to be along the same direction, you get the traditional collapse. You collapse either to one state or the other of the two-state variable. But if I start making those measurements fight against each other, I start changing the angle between them, what happens is something quite remarkable. I'm measuring like crazy, but I don't get collapse anymore to single states. I get a kind of diffusive process where I start smearing out this collapse point to this collapse region. And when they're maximally fighting each other, when the x and the p are maximally opposed, you simply get diffusion along a circle. So there's no collapse. You can measure forever here, and you simply get diffusive process. I think it's quite remarkable and beautiful. And indeed, this is done in the experiment. There's a neat trick with the experiment, and especially for the quantronium folks. that if you have, the way this works in the experiment is you have a single quantum bit here, but you connect it to two different modes of a three-dimensional cavity. And so by exciting both of them, you can put one of the output modes at a node of one to be able to extract just one of the outputs, and then be able to then selectively measure by putting sidebands on this one or both of these quadratures. Okay. So this gives new insight into the nature of Heisenberg uncertainty when I have continuous measurements jointly of non-commuting variables. I mentioned in my cardinal properties talk or slide that it's possible to reverse a quantum measure. How does that work? How could you possibly reverse a quantum measurement? And here's a nice little experiment, thought experiment, which has also been done in the laboratory, and so one guy is the other. And the idea is I talked to you before about this quantum point contact measuring a double quantum dot. And the idea is that what I can do is I can measure the integrated output of this measurement in a single shot. I turn the detector on for some time. I collect some random, seemingly noisy data, and I turn the detector off, say, at the blue line here. I'll get some result or not. Now, how could I, and we've learned that will disturb the quantum state of the system. It will disturb it. How could I possibly undisturb it? Well, I can't microscopically reverse it. I've already collected this data. This is sitting in my detector. But what I can do is I can do something interesting. I turn the detector back on. I collect data, and eventually I wait for this measurement result to come back down to the 0 point where it started. If it does that, I turn the detector off, and I claim that I've reversed my quantum measurement. You see? How could it possibly work? And the idea is schematically given here. What's interesting is you don't need to know what this initial state is. It can be anything. You start here, you do this partial collapse, you get to some state which you don't know, but then you do this second uncollapse procedure like I showed you here. And what's interesting is that sometimes this will come down and cross the line, and then I succeed. I get a green light, and I restore the initial state as the claim of the theory. But it may not come down here and cross this line anymore. It may continue to go up, 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 up. In that case, you fail and you give up. So it's a stochastic reversal. That only happens some of the time. But I can then say with certainty when it happens and when it doesn't happen. Okay? So this is quite interesting. It tells us that we can actually reverse the effects of measurement by waiting until the second measurement essentially nullifies the information from the first measurement. Okay? So this has also been verified in experiments as well. The interesting catch is, it turns out that the stronger the measurement is, the longer I do this first measurement is, the more and more unlikely that this will happen. And so it recovers the traditional statement of irreversibility only in the ideal projective limit. Okay, and then we can be talking about how do we use this to build quantum technology, how do we build amplifiers. We have a whole chapter on using Josephson circuits to build 3-wave mixers, 4-wave mixers, traveling wave amplifiers, a lot of nitty-gritty details that I think will be also be of interest to the experimentalists as well. Okay, and then once we understand the physics of measurement, we can then begin to talk about, once we understand how this works, can we then be able to then control and intervene in the quantum world, be able to make the quantum systems do what we want it to do, okay? So this is a really nice example about using feedback and control to control the quantum system. So this is an example of continuous quantum error correction. So suppose I have 3 qubits that I encode a logical qubit in. For example, I can prepare the state alpha 000 plus beta 111 as my logical qubit. And then I suppose one of the qubit has fluctuations with the environment. Say it flips. It goes from 1 to 0, 0 to 1. How could I detect that and maintain my logical qubit without destroying? Okay, and the traditional way you would do this is by making an ideal parity measurement on both or 2 of these qubits. I would check the parity of, say, these 2 and the parity of those 2. What do I mean by parity? I simply mean, is the quantum state of those subsystems, is it in the 0, 0 or 1, 1 subspace? That would be even parity. Or the 0, 1 or 1, 0 subspace, that would be odd parity. And so if I just know the parity, I don't disturb the coherence of the system. Okay. And the way that this is actually done in the experiment is we change the physics of this. We simply couple a resonator to both of these qubits such that the resonator is either strongly on or off resonance. And so depending on the parity of these systems, I either get a phase shift of 0 or pi. Okay? And so in the experiment, what can happen is we turn on both of these continuous parity measurements, and this shows the quantum trajectories using the resonator of these voltage of one resonator or the other. And most of the time, it's down here in this no error subspace. But occasionally, it wanders over here. For example, there's a qubit 2 error, and when it crosses some threshold, we can then apply a control pulse to bring it back. We flip one of the qubits based on the syndrome here and bring it back to the 0 space. So there's 3 possible errors, and we can bring all of these back to the subspace. So it's quite a nice example of continuous measurement that we're monitoring all the time for errors and being able to correct for them in real time. Good. Okay, and then we finish the book with this epilogue. Many people like to talk about philosophy of quantum mechanics, and we give our perspective on what it all means. And we have some, but we're very clear that everything has been scientific. Everything has been based in laboratory findings, mathematical description, but we allow ourselves the liberty to talk a little bit about philosophy in this last chapter, with the understanding that this is more of our take on both on the field and what we've learned from this book. Okay. So let's talk. I've got maybe another 10 minutes or so. Let me talk more about the last subject I want to tell you about, which is the most likely path and how to use that in optimal control theory. So what is the idea? So the idea is that we have some quantum system, for example, an atom. We have a continuous monitoring device. For example, this might be monitoring the spontaneous emission from that 2-level atom. But we also have some control. I can drive this. I can apply a microwave frequency drive, or if this were a natural atom, this would be an optical frequency drive to create some superposition here to drive the quantum state around as we like. And the question that we want to do is we want to, first of all, let this control parameter be some arbitrary control. It's time dependent. And I want to be able to say, suppose I have something I want to do. If I want to say, as I'm monitoring this quantum system, I want to find the optimal control parameter to move the quantum system, say, from an initial state to a final state in some time. That could be the goal I want to do, right? So like in the classical physics, I want to take a car. I want to start in my house. I want to end here at the laboratory. I want to minimize the time. What's the correct sequence of controls I need to give to get me from point A to point B? So I can have an analogous kind of statement of the problem for quantum systems. And it's not simply a Hamiltonian anymore because I've got continuous monitoring, so I can take into account the fact that there is this quantum measurement back action going on. So what do I want to do is that given this noisy system dynamics, I want to optimize over the probabilities of the outcomes. I'm not going to do feedback here as a cost function. So the cost function is I want to maximize the probability of getting from point A to point B in some time t. This is closely related in classical physics or classical control theory to this Pontryagin maximization principle, which engineers have been studying since the 1950s. So the idea is to try to marry some of these classical control theories with some of our quantum measurement approach theories. And the way we approach it is we take our stochastic path integral I was telling you about before, and again, I'm getting more into the mathematical physics side of the story. But we rewrite it in terms of these operators. So rho is the conventional density matrix, which is what we call the quantum state. The sigma here is something we call the co-state. That's kind of like that canonical momentum I was talking about before. Now this is an operator formalism. So this would be the action rewritten of the stochastic path integral. And the stochastic Hamiltonian has a piece that involves the quantum state dynamics in the co-state, as well as the log likelihood of the outcome of the measurement. So what we're doing here is we're weakly measuring or continuously measuring some operator L of the quantum system. It might be, for example, the sigma z of a two-state system, or it could be something more general. And what we're going to do is we're going to introduce some time-dependent control parameter, chi of t, in our description. So now our equation of motion becomes chi-dependent for these variables. So this v is now L squared. The delta is some variance operator. and we have some anti-commutators here. R is the readout, which also becomes parameter dependent, so it becomes more complicated. That's the quantum state dynamics. This would be the co-state dynamics. That's like the conical motion for the conical momentum. And then we want to try to start optimizing it. We want to optimize our action as a cost functional, given some boundaries, some constraints. So I want to start in some state rho. I want to end in some state rho f in some time t, for example. And then I want to optimize this action functional such that I can then derive an equation for the optimal control parameter chi of t that does the job for me in this optimal way. Okay. So these are the optimal path equations for the state and the co-state, and this allows us to derive the optimal time-dependent control parameter. So this would be presumably optimal stochastic Hamiltonian once I optimize over the readout. So how does this work once we have this mathematical formula? And maybe it's interesting to point out, if you look at these, this looks actually very interesting. This is sort of like the quantum state dynamics forward in time, whereas this looks a little bit like the quantum state dynamics backwards in time. So there's an interesting kind of, this kind of picture going on here. So here's a simple example that we worked out. Suppose we take our paradigmatic simplest system of a quantum harmonic oscillator. I set the frequency to 1 here, and here's a little physical implementation of that. I could, for example, have an atom in a cavity where I probe it, or I can even just have the cavity mode itself as the probe, and then I can amplify with a local oscillator one quadrature here in a homodyne detection scheme, where I have the freedom. I have the freedom that I can then put a local phase in front of one of these detectors, so that I can amplify either, for example, the one quadrature or the other quadrature, which is like amplifying either the position or the momentum. It's like doing a position measurement, momentum measurement. Or I can actually do it somewhere in between. I can measure a quadrature that's sort of 90 degrees, or whatever angle I want, just by being able. So the control parameter here would simply be the relative angle or the phase shift I would put it here before I measure. And so I'm going to think about this angle as my control parameter. So I can amplify this quadrature operator, which is some weighted composition of position and momentum. Okay. And then there is some orthogonal quadrature m, and then the readout that I would get from my homodyne detection would be the expected value of this quadrature plus some noise. And again, that tau is that characteristic measurement time I was talking about earlier, telling me how strongly I'm measuring. And for this simple example, I can solve the path state and the co-state of the previous equation. These two guys here, I can solve those two equations together with an equation for r of theta. And so you see, I don't actually need, if I go back, I don't actually need the co-state equation if I can figure out what r of theta is, because sigma does not appear in this equation, but r, the optimized r does. And so if I can do that, so I can then write other equations down for r that I can solve exactly as these coupled dynamical equations where I define these parameters v, w, and z here. So by solving this set of coupled equations together with my state and co-state equations, I can then derive what the optimal control is to move me from one state to the other. Okay. So then what I'm doing is I'm marrying now this Pontryagin control principle with our optimal path, because the optimal path essentially extremizes the probability of those states. And so this is indeed the quantum version of the Pontryagin maximum principle. So here are some example results. So I start, for example, in some state. So here what I'm doing is I'm taking a squeezed coherent state. There's some other squeezed coherent state. This is an oscillator as a function of time. Just for simplicity, I don't give you the variances. I just give you this is the x quadrature, the position. This is the p quadrature, the momentum. And with the control, my starting point is the blue dot. My ending point is the red dot. And so with a certain control that's given down here, so this is my theta control, I can indeed drive it from here to here in time t. Okay, so it works if I apply this weird control parameter to the quantum system. Okay, not to the quantum system, to the measurement device. Right? So I continuously change that angle in this weird way, and that makes the system drive along the way I want it. So it works. Great. But some weird things, surprising things happen I didn't expect. For example, you can say, suppose I don't do any control I want, but I can only do control, say, between minus pi over 2 to pi over 2. Okay? What happens in certain cases is that on the right-hand side, we actually go to some squeezed, another squeezed coherent state. And you see here the scales on the right and left are different. So if I go from here to there, I can indeed get the correct behavior that I want, but look what happens to my control. My control is something really weird. I have to do something like down, up, like that. So this is called in literature bang-bang control. People have just applied this in kind of ad hoc way previously, but we see here from this maximization principle, this kind of control very naturally appears in a wide range of problems. So you have this very instantaneous jumping of the control as a function of time to get you where you want to go. So there's something that was quite surprising to us. Okay. Maybe I'll just say, just to finish up, people said nice things about the paper. Chris Fuchs made a nice comparison to Wheeler's philosophy and says he thinks that this is the first living instantiation of Wheeler's deep thought coming to physical practice, which was nice. Here closer to home, you all know Jean-Michel Raymond from the Sorbonne. He also says very nice things about the book, which I was very pleased and honored by as a valuable reference. And then also Gerald Milburn, who is also a leader in the field, also said very nice things and makes an interesting point touching to some of the foundational aspects, which I was interested in. He says, yes, in doing so, they recast moribund questions in quantum foundations and provide the tools for more effective quantum technology, which I thought was very thought-provoking and interesting. And of course, Gerald also has written a very nice textbook on quantum measurement theory that has been sort of the reference. Maybe a word about the cover. The cover is kind of a fun human interest story. I got my brother to draw me the cover art. And what he did is he took this superconducting circuit from the Berkeley Nanoelectronics Laboratory, and it reminded him of these two artists, Frank Stella and Joseph Albert. Joseph Albert basically had his whole career making little squares of different colors. He was a big square guy. And Stella was basically, his whole thing was making little curves. And so Peter essentially combined Frank and Joseph's artwork to make this beautiful cover design. Nice little human interest element. Okay, and then this is it. So I told you about some of the recent advances in quantum measurement theory and practice. Talked about some new results in optimal control theory. And if you buy the book, I hope you like it and learn a lot from it. And thanks to, of course, to everyone that has worked together with us over the years, including especially my co-author, Irfan Siddiqui. And if you want to buy the book, you can get it anywhere you want. Thanks very much.
So you state very clearly what was inside the book. Can you say what is not in the book? You very shortly mentioned the last chapter. Do you think you have tried to cover the question of the measurement problem, or do you think you have tried to avoid it and strongly say that you don't want to speak about it?
So I think, okay, so I have two answers to your one question. The first question, as I mentioned in the beginning, we're very much focused on the physics of measurement. You do this, you probe that. What happens in the laboratory? That's our job as physicists, is to describe reality as we see it. That's the focus of 95% of the book. Then there are other questions. Can you go further? Can you go further down that line of thinking? How does this break down? Can a measurement device be quantum? Where is this transition between classical description and quantum description? We touch those questions in the conclusions in the epilogue chapter, but it's really only a very cursory discussion. The point is that to have a proper discussion of quantum foundations requires a whole nother book, because there are so many different camps and warring philosophies, And we just didn't want to go down that route. We wanted to say, just touch a little bit on it, but didn't say too much about it. So I think that is my answer to your question. But in terms of other things, what do we not cover in this book? So this is, again, a selection of the topics we thought were maybe most important for students and colleagues to know about. But the field is vast, so we didn't cover things like interaction-free measurements. We didn't cover things like, I didn't do anything really about quantum metrology. I did a little bit of quantum metrology, but they're really, we think about if we do a second edition, maybe we have a whole other 2 or 3 chapters on quantum metrology. But there are many other things that we don't talk about. But that's natural for any book. You have to have focus, otherwise it becomes an encyclopedia, right? Which we did not want to write.
Nevertheless, could you tell a bit more on what's your opinion on the present issues of quantum foundations of quantum mechanics?
Yes, well, I think there are many open issues. In fact, I was telling Joseph, we just got awarded a Templeton Foundation grant devoted exclusively to doing quantum foundations topics. So I think there are many interesting things. And even this topic that I was telling you about before, about this optimal control theory, I think the fact that we can think about this one state moving forward in time, the co-state moving backward in time, I think that gives us a hint something deep is going on there. That can tell us something about the foundation of quantum mechanics. One of the other things that I'm really interested in is the idea of agency, the fact that we have the freedom as observers to turn on knobs whichever way we want. We're not forced by nature to turn on knobs one way or the other. We believe we have the freedom to do that. And the fact that we have that freedom, what do we choose to measure, then changes the quantum system, right? So the fact that we have agency somehow seems to impart a reality of the quantum world. And so going further into that notion, how does that work? Is there something called a quantum agent? This is something we're trying to think about. Could you have an agent that exists in quantum superposition, doing different actions together in superposition? I think it's a fascinating question. I just don't know. But I think there are many open questions that can further be elucidated. And so those are a couple of them, but I think there are many more.
And do you plan to test the causality?
Yeah, so this is a very deep problem, right? So we mentioned this in the book. We talk a lot about Bell inequality because the most natural thing is to say quantum physics is simply a statistical description of a deeper fundamental underlying theory that we just don't know yet, right? Just like statistical physics is an effective description of a microdynamics we simply can't see, right? The problem with that program is that the Bell type of inequality arguments really put very, very severe constraints on the kind of more fundamental theory you could have. And so that's one of the, so it's a really good point. So that's one of the really more challenging things if you want to come up with another theory beyond quantum mechanics. And indeed, we talk about a post-quantum science. What does post-quantum science look like? Right? We've had quantum mechanics for 100 years. No one ever promised you it was the gospel truth. There could be a deeper theory, and having that deeper theory would be amazing, right? So, but even our most fundamental theories or speculative theories, like Joseph works on string theory, right? That's still based on all the quantum formalism. Maybe quantum mechanics is just not right at some point. There's something else we don't know about. Science should allow this possibility. We should be able to pursue those ideas.
Yeah, just another question. So regarding those trajectories you mentioned and talked a lot about, so is it correct to understand them as, say, if the trajectory goes one way, then and happens to be in one point at the moment, then that means that if we were to make a projective measurement, a strong measurement in that particular direction, we would always find results plus one? That's what.
Good question. So yes, we have the trajectory. We have a single run of the detector. It's doing something like this. Now stop now. The prediction is this. And so indeed, if I test that, if I do sort of a standard traditional measurement at this point, indeed the prediction should be that state correctly describes the state. Now remember that state is not a deterministic prediction. It's a statistical prediction. So that means I need to measure that state in principle many times in different degrees of freedom to test that that is a correct description of the outcomes at that point. For example, if I were a qubit, I would make a bunch of X measurements, a bunch of Y measurements, a bunch of Z measurements, and check that the frequencies of those results match the prediction at that point.
Couldn't you just do a measurement in that particular direction?
You can, but I think for the experiments, it's simpler to do the other point of view. And then you say, well, how do you come up with all those different realizations? And the answer is actually a tour de force from the experimentalists. If I go back to some of these things, what they do is actually really amazing to do this kind of stuff. Let me see if I can find. Yeah. So this is actually an example of one of these curves is a single realization, and the dashed line is the tomographically validated realization. What they do is they create some huge database of every possible state over like millions and millions and millions of these experiments, and they come along and then find all of the experiments that predicted this point in their span of lifespan, and when they measured at that point, that gives them their ensemble to check all the different states to make sure that that's actually a validated point. So does that answer your question?
Yeah.
I'm a bit confused. Can I rephrase if I understand correctly? What if, okay, let's take a simple example. You have something on sigma x and you let it go, and it goes at some point on sigma z, that's the final state. But at some point, maybe it ends up being just an eigenstate of sigma y, slammed there. Then if I measure things in the y direction, I'm going to get 1 plus 1. I'll never get minus 1 there.
That's correct. Yeah, that's right. So you would need
to explain in that language because I'm just more...
That's right. So if you measured only the y degree of freedom,
yes,
you would get y is plus 1 every time, right? And if that were the case, you would need to do also the z and the x measurements because that's a pure state along y, right? And so that would be sufficient. But that's assuming that it's going to be along y, right? But generally it's some general state. And so if you knew
so what is tracking? Don't you follow the ways? Don't you follow the state?
You do, but then you ask, you're following the state, but then you could do that experiment, but then you'd have to, when you got here, you'd have to know what the prediction is, and then either tilt the state along the axis so it's aligned, for example, z, if you only do z measurements, and then do that every time. So you have to do a different conditional rotation every time to be able to do that kind of experiment. And that's very challenging.
Oh, I see. But
that's very challenging experiment.
But it's an experimental problem. It's not some.
It's right. It's an experimental issue.
Okay.
Exactly. So experimentally, it's easiest just to do all these standard tomographies. Yeah.
Actually, I think following up on that, I still haven't really understood how you're able to perform these single shot measurements to, as a spectator, right, follow those trajectories without inducing a quantum jump every time, right?
Yes. So this is, remember I talked about there are two kinds of continuous quantum measurements. One is the diffusive kind, and one is the jump kind. In both the cases, you're getting measurement back action. By doing the measurement, you disturb the state. And that's what this jitter is. This is the disturbance that's happening all the time when you're measuring it. That the measurement induces that noise. Okay? And so that's part of the thing. If you just look at the measurement signal, it looks like just some noise. You say, this is just junk. No. The noise is the signal.
Okay, thanks.